Hello everyone, my name is Kline and I am an undergraduate student in the Department of Chemical and Biological Engineering at the University of New Mexico. Thank you for attending my final presentation on computer characterization of the potential formation of galvanic coupling following the processing of automotive parts. First, I would like to thank my faculty mentor, Dr. Ramiro Castanero Lopez, and Texas A&M University for providing me with this opportunity to present my research. And also thank our sponsor, the Center for Research Excellence on Dynamically Deformed Materials. This work was supported by the Department of Energy, National Nuclear Security Administration under award number DENA 0003857. Now, manufacturers have been switching from thin, high-strength steel to aluminum because of its lighter properties. Aluminum increases performance and efficiency while decreasing fuel consumption. But with change comes considerations. Aluminum has the potential for galvanic coupling at the welding points. Now, what is galvanic coupling? Alone, aluminum may not corrode, but when combined with another material, it will have an electrochemical reaction. An electric current will flow between the two metals, which will hasten the corrosion of the anodic metal and in turn cause the cathodic metal to corrode. This reaction is called galvanic coupling. You might recognize this as galvanic corrosion. Now, where do we begin in this research? When starting, I had to ask a question. How do I know what materials to use and which ones work well with each other? Now, the type of aluminum used in the automotive and aerospace industry is aluminum 7075-T6. Looking at the anodic index, the less difference in the anodic index, the more galvanic compatibility, or the less effects of corrosion. There are three categories of environments to consider: harsh, normal, and controlled. If you want absolutely no galvanic corrosion, the values above show that harsh needs to be less than 0.15 volts, normal needs to be less than 0.25 volts, and controlled needs to be less than 0.5 volts. This means that only under a controlled environment will there be no galvanic corrosion. However, we are not normally under controlled environments, so the closest values to achieving the least amount of galvanic corrosion will be with either zinc or galvanized steel at 0.3 volts. And throughout my timeline, I used a research plan to match, simulate, then evaluate. I did this by matching the corresponding materials with aluminum. I then used GIN 3.3 to create simulations to confirm the potential formation of galvanic coupling. I was able to evaluate the graphs to find the earliest points of galvanic coupling and find which ones would truly have the shortest corrosion rate. I planned on using this information to cross over into the OLI Studio Analyzer software to analyze if this material match would sustain throughout all environments throughout the United States. However, I found that the OLI software was limited to only pure aluminum. Therefore, I changed my goal 5 to see if the change in environments from the increase in road salts and pollution had any effect on corrosion rates of pure aluminum. I was surprised by my results. As mentioned earlier, I had to find the best material combinations with aluminum 7075-T6. I did this using GIN 3.3. Aluminum 7075-T6 with a BSAA coating and an anodized seal chromium 6 plus treatment is an ultra-high strength aluminum alloy that already contains zinc and is highly used in the automotive, aircraft, and aerospace industry. Once I created the simulations, I put all the data into a Microsoft Excel spreadsheet. There I was able to find the information I was looking for. Look at the cathode galvanic acceleration factor, which is located 7 columns from the left, and notice that there are only 2 potential possibilities. I highlighted zinc as having the lowest corrosion rate with the lowest cathode galvanic acceleration factor for this reason. Now, zinc is the best option because we are looking for a redox reaction where aluminum is the cathode and the fastening material is the anode. The anode acts as a protector of the aluminum. As you can see in the graph on the right, the cathodic protected side of aluminum crossing with the anodic active side of the zinc is at 4.54 e to the negative 4 amperes per meter squared. Now, what we don't want is for the aluminum to be on the more active side where it'll start to corrode on itself, as seen in this example in the chart when I matched it up with nickel. Now my next step was to use the OREUSummer software and to see how the changes in our environment affect our chosen materials. Since I was limited to my material choices, I focused on pure aluminum. As you can see on the map on the left, in the more populated areas of the United States, there is an increase in acid rain, which means a decrease in pH, and this is because of the atmospheric pollution or particulate matter. The same map also shows a heavy usage of road salt in obvious separated regions of the country. On the right is a more detailed map of the salt usage, which I use this information to narrow down into a percentage of salt increase that's exposed to a vehicle. Now, this map shows the separated percentages per region. I use these percentages as my environment conditions in the OREUSummer software. In the southeast, even though I know that there's no road salt usage, I ran it under 3.5% NaCl conditions due to the coastal seawater. I also ran a separate simulation under acidic rain conditions. Surprisingly, with an increase of salt, there were no change in the current density, which means there would be no change in the corrosion rate because aluminum is passive. However, if the pH changes, then the corrosion rate will most definitely increase. After this discovery, I went further and continued to do simulations to analyze an addition of pH as a variable. What would be a change in the current density because of the local attack from the pH? Now, before I go on, I need to mention that in the next following simulations that I'm about to show you, there are not realistic conditions except for the percentages of salt exposure, which I used in my previous research. The values that I used for the increase in sulfuric acid to get drastic levels decreases of pH were done only to see if there was an obvious reaction. In the real world, we will not be exposed to 100 milligrams per liter or 200 milligrams per liter of sulfuric acid. So here, the most obvious result was when there was a 79.98% of NaCl increase, which was simulated at the road salt exposure in the northeast of the United States, with an addition to any form of sulfuric acid added to the in-stream. According to the simulations, when exposed to acidic rain conditions, which means it only has 31.85 milligrams per liter of sulfuric acid, as NaCl increased, the corrosion rates would also increase. Only the simulation with seawater at 3.5% NaCl, with an addition to a change of pH using different in-stream amounts of sulfuric acid at 31.85, 100, and 200 milligrams per liter, showed a plot change. However, at the other percentages of NaCl, a change of pH kept the current density at a constant rate. I would be most interested in seeing if there's an effect on the corrosion rate once zinc is brought into the picture. I will have to leave that for further future studies. During this research, we have found aluminum 7075-T6 fastened with zinc 99.99% as the best combination for the automotive industry. The simulations have shown that with an increase of NaCl, the current density of pure aluminum does not change. However, a change in pH will certainly expedite corrosion. And once NaCl and pH are combined as variables, corrosion will be expedited even further. I can now say with certainty that pollution is highly corrosive to even our most passive materials, and we should do our best to take care of our planet. However, I still have questions remaining. If zinc is the best combination with aluminum, does that mean it's the best combination throughout all environments? Can it withstand the pH of acid rain and provide the protection that aluminum may need? If given the opportunity, I would like to further my studies and continue this research to find out the answer to my most pressing questions. Now, the following here are the references that I used throughout my research. And now I would like to thank the rest of my team, Dr. Raimundo Case, Kalani Wilson, Ramon Sanchez, and Nina Casilla for their teamwork and support. And I would like to thank you all for listening to my presentation. And have a great day.